Hello students, in this video we will discuss what is Baye'S theorem and how to prove Baye'S theorem. Let us start. Observe the statement first. If A1, A2, A3, so on, An are mutually exclusive and exhaust to events in a sample space S, and each probability is a positive, E is any event in the same sample space S, and probability of E is also positive, then prove that probability of AK given E means probability of occurrence of AK after the occurrence of E. This is conditional probability equal to probability of AK into P of E given AK by sigma I equals to 1 to n P of AI into P of E given AI for some k value 1 to so on n. Here AK means any one of the event in 1 to n here. This proof will start with A1, A2, A3 given actually mutual exclusive and exhaust events. We are going to start this first line. This is sample space S, and what are given here? A1, A1, A2 and so on. An are mutually exclusive and exhaust events. Therefore, here are the A1 I am writing. See, observe this diagram. A1, A2, A3 so on An. These are mutually exclusive and exhaust. A1 there is no intersection between any two and so on An. So total sample space we are dividing like this A1, A2, A3. There is no intersection in between any two. That's why these are mutually exclusive. And a whole union of all these events nothing but S, because exhaust events also given. That implies I am writing mutually exclusive means there is no intersection between any two of the events. That's why AI intersection AJ equal to null set 5. I is not equal to J. What about IJ? IJ lies between 1 and n. That is 1 less than or equal to I comma J less than or equal to n. That means A1, A2, A2, A3, A5, A6, A6, AN. There is no intersection between any two events in the sample space. That is 5. And next, I am taking any other event E is there in the same sample space S. This is E. I am taking this event is E. Here one more point is there. A1, A2, A3, so on, AN are what type of events? Exhaust events. That implies we can write A1 union, A2 union, so on, union, AN equal to S. These 2 points mutually exclusive. That implies I am writing this step. Exhaust two events. That implies I am writing this line. Now we have to discuss about E. E is any event in the same sample space S. And what this is the region. What about this? A1 intersection E. This is A2 intersection E. This is A3 intersection E. And so on. This is AN intersection E. All are again mutually exclusive. There is no intersection for these two. Observe this. So each is mutually exclusive. A1 intersection E, A2 intersection E, and so on. A3 intersection E, and so on. AN intersection E are mutually exclusive also. That implies I am writing A1 intersection E comma A2 intersection E comma and so on AN intersection E are mutually exclusive events. Next, now I am starting with, we know that how to remember this step. E can be written as event E can be written as E intersection S. This is sample space S. This is E. So E intersection S is nothing but E only. That implies applying P on both sides, probability of E we are finding, probability of E intersection S. Now what about S? Already we know E intersection. Clearly S means what is S? A1 union, A2 union, so on union AN is S. Instead of S I am writing A1 union, A2 union, so on union AN. Instead of S I am writing this line. E intersection S. S place I am writing this part. Now this can be written as P of E intersection A1 union E intersection A2, E intersection A2 and union so on union E intersection AN. See, I'm writing E intersection A1 union E intersection A2 union so on union E intersection AN. Now already we know these events E intersection A1 comma E intersection A2 comma E intersection AN are what type of events? They are mutually exclusive events. According to this line, they are mutually exclusive. That's why this union place we can write plus. By axiom of additivity, union place we can write, this is one of the property, axiom of additivity. Instead of union I am writing plus. P of E intersection A2 plus, we are writing P for all brackets, and instead of union I am writing plus. By axiom of additivity, this is the property. So probability of E intersection AN. This total step we can write simply with the help of sigma like this. I equals to sigma I equals to 1 to n probability of E intersection AI. Simply you can write like this. This is probability of E. Now observe the statement. See, this is last line. What about LHS of the Bayes theorem? Last part. Probability of AK given E. I am starting with this LHS. LHS equals to probability of AK given E. This is conditional probability. By definition of conditional probability, this can be written as probability of AK intersection E by probability of E, because by definition of conditional probability we can write like this. Once again, numerator place we can write P of AK intersection E can be written as probability of AK into P of E given AK. This is also formula. Why? By definition of multiplication theorem. Numerator value is by definition of multiplication theorem I am writing. Definition of multiplication theorem on probability. Multiplication theorem on probability. Numerator as it is P of AK into probability of E given AK by probability of E. What is probability of E? In the previous step, we have P of E. P of E equals to sigma I equals to 1 to n probability of E intersection AI. So in the place of P of E, I am writing sigma I equals to 1 to n probability of E intersection AI. Now this equals to probability of AK into P of E given AK by sigma I equals to 1 to n. Once again by multiplication theorem, this can be written as probability of AI into probability of E given AI. Once again, since by multiplication theorem on probability. Multiplication theorem on probability. I have to mention this. This is RHS. That's all. LHS here, RHS.